All right, so we are active, we are recording. Welcome. Here we are, private pilot ground, and we're on the 6th of April. We just had ourselves a test since our last meeting. We're seeing a lot better test scores using this digital format. Today, we're going to spend some time going over the test. After we finish going over the test, especially hitting some of those tricky problems that some of our students were talking about a few minutes ago before we hit record. Then the next step will be to start moving into weather, which will be our next chapter, chapter 6. So before I click us over to Blackboard and start looking at to review the test we just took, if there's any other open thoughts or open questions from the group, now would be a great time to bring them up. All right, so I'm going to click the button to start sharing our screens. And at this point, you all should be seeing my Blackboard. This says, this is our midterm, chapter 5, the test that we just took. So let's try to make it just the right size here for everybody. Cool. All right, so this was one of the questions right here that a lot of y'all are having trouble with. So this question right here is one of the more tricky questions for the test. It says we need to refer to figure 82, and I should have already had the figure supplement open. So just so you can watch how it's done, you can go to the FAA website. So if you need a copy of the testing supplement, you go to the FAA website. Here in the search bar, we'll type test supplement. And this is what's going to give us the list of figures and legends, computer test supplements. Today we are working on private pilot. So this the same testing supplement that they use for sport pilot is the same as private pilot. So we found private pilot in that list, and it might take a moment for this supplement to load up. It's a large PDF document with all the figures and legends. Basically, what's going on in this last question, this first question, I should say, is that we are learning, we are reviewing some basics about what altitude to fly based off of what direction we fly. So there's actually a famous aircraft accident that happened over the Grand Canyon. Some of y'all have been sending me emails, so I've been responding back that way as well. Here we are together, and there was a famous aircraft accident that happened over the Grand Canyon, mid-air collision style, where there's two aircraft and both airplanes are looking out the window at the beautiful Grand Canyon below, not paying attention to what's going on in front of them, and they actually had a mid-air collision. So years and years ago, very famous accident over the Grand Canyon, and that's when it was determined that we as pilots should have different altitudes for different directions of flight. This is a very famous regulation from Part 91 of the regs. Remember Part 91, General Operating Flight Rules. And this famous regulation is called VFR cruising altitudes. I was always taught a phrase called odd balls fly east. Odd balls fly east. Maybe you have a flight instructor named Ryan Allball, and maybe that helps you out. So odd balls fly east, ODD, odd balls. So the idea is that if you're at an odd, if you're going to go easterly, then you want to choose more of an odd altitude. You know, think things like 3,000, 5,000, 7,000. But wait a minute, we as VFR pilots are plus 500. So we are plus 500s for VFR cruising altitudes. So if we want to fly a cross-country flight easterly, then some of the appropriate VFR cruising altitudes could be 3,500 MSL, 5,500 MSL, 7,500 MSL, 9,500 MSL. Those would be some appropriate VFR cruising altitudes if you're flying easterly. Oddballs fly east. If you was going to go fly westerly, then you would have to be an even plus 500 altitude. Then it could be something more like 4,500, 6,500, 8,500. So it looks like our testing supplement's starting to load up. So hopefully we can analyze how to apply some of those rules a little more clearly. It says we need to analyze figure 82, altimeter number 3. And then we need to figure out what course direction is appropriate for this VFR cruising altitude. So let's see if we can find figure 83. Figure 17, wow, we got to go way farther. Figure 51. We're getting closer. So what you're going to learn is that the VFR altitudes are plus 500. And then later on, when you become an instrument pilot, you'll fly at the 3,000, 4,000, 5,000, 6,000. Whereas the VFR pilots are cruising at plus 500s. So the VFR pilots cruise at plus 500s. We're getting really close. We're looking for figure 83. We're fighting technology, hoping that it loads up for us. Here's figure 74. Goodness, let's keep pumping down. This question is also going to be a fundamental exercise of how to read an altimeter. So we're really close. Let's keep going farther. We need figure 83. You can find exactly what you need in those PDF documents. Hold Control F. Type figure. So I hit Control F and we type figure 83. Okay, so let's see, what did I do wrong? Figure 82, we were one off. Last one in the book. All right, so look at this nice looking PDF. And we were supposed to look at altimeter number 3. Man, it's kind of sideways, huh? Do we dare click the rotate button? There we go. So remember we covered this in chapter 2, how to read an altimeter. And so just like reading a clock, you know, the big hand, the little hand, the hours hand, second hand, we are now looking at an hours hand, or if you call that thousands, we're at 9,000. So that's 9,000 feet. And here's more of your minutes hand, call that your hundreds. So you're 9,500. This would here be more like 10,000s, this very narrow. The last hand, it's very short and stubby, and then it turns very thin. It is less than 10,000. So if this hand continues to increase, then our altitude would be over 10,000. But in this case, it's still less than 10,000. So this altitude is showing us 9,500 MSL. So altimeter number 3 is 9,500 MSL. So when we study our test question, it's telling us that the course direction appropriate for flight would be an easterly. The oddballs fly east, part 91. And so that's why we're getting the correct answer of 080 magnetic. Why is incorrect? Because it says true. So VFR cruising altitudes are based on magnetic, not true. So magnetic course, not true course. Why is answer choice C incorrect? Well, answer choice C is describing magnetic courses between 180 and 359. That would be more of a westerly course. So the best answer choice here is A. you know, we had a lot of questions on this test. So if you think that, you know, this one was unfair or too tricky for us, you know, things of that nature, but this is a fundamental question that you're going to have to be ready for private pilot written exam. It combines some elements that we've learned about before with reading the altimeter and some newer elements dealing with cruising altitudes. So that's probably one of the trickier questions on the written, that the test that we took, that I'm getting responses from. All right, I'm not really getting a whole lot of feedback, so I guess I'll keep moving here for us. We have a good question, except for necessary for landings or takeoff. What's the minimum safe altitude required for the pilot over other than congested area? So other than congested area. We're not over the big city. It's other than congested area. So we're 500 AGL, except if it was open water, sparsely populated area, the desert, the ocean, which would just be 500 feet from any person, vessel, structure. So remember, minimum safe altitudes, part 91 question, minimum safe altitudes, other than congested area. So it's 500 AGL. The answer choice B, that would be the answer if it said, what's the minimum safe altitude anywhere? And C is actually giving you incorrect numbers. So that's a distractor putting wrong numbers. Number 3, we're approaching to land at an airport without an operating control tower, Class G airspace. The pilot should make all turns to the left unless otherwise indicated. So you just need to know that standard traffic pattern is 1,000 feet AGL left-hand turns. I had a lot of y'all, I've been grading the tests. I'm not finished grading everybody's since there were some people really put off to the last minute last night. But I've probably gotten through a handful of them, and I'm seeing some incorrect responses from some of the tests for answer choice B. So answer choice B is not the most correct because our standard traffic pattern is 1,000 AGL, not 800 AGL. Yeah, there are some airports that could have an 800-foot AGL traffic pattern, but the standard traffic pattern is 1,000 AGL left-hand turns. So that's the best choice here according to our FAA test bank. Question A. Make all turns left unless otherwise indicated. Answer choice A. All right. We're talking about airworthiness certificate. We're talking about legal documents. This would be a chapter 1 question. A lot of us remember AROW, A-R-O-W, airworthiness, registration, operating limitations, weight and balance, legal documents that must be kept aboard the flight. And so in addition to the airworthiness certificate, we need operating limitations, which would typically be the POH, and then registration certificate. And then like we learned, there's actually 2 registrations aboard the aircraft. One's for federal and one's for state. On the day of your private pilot check ride, you must know that answer to get through the oral exam. And the examiner will want to know that federal and state, 2 different registrations, expiration dates, 1 year and 3 years. We got an aerodynamics question here for us from our aerodynamics section. An aircraft leaving ground effect during takeoff will experience an increase in induced drag and a decrease in performance. So this is the exact same question that's been put on our midterm that we had on our earlier chapter test. It's a tricky question. And remember ground effect, it's reduction of induced drag when you are within 1 wingspan of the ground. Free lift without the drag penalty. We have so when you leave ground effect, when you climb higher than 1 wingspan, we have an increase in induced drag. Remember wingtip vortices, downwash, and we have a decrease in performance because drag hurts our performance. We got a question here about load factor. I had a lot of y'all missing this question here. The amount of excessive load that can be imposed upon the wing of the airplane depends upon the speed of the airplane. So remember that maneuver speed is an important placarded speed in our aircraft. If we are at or below maneuver speed, if we are at a slow airspeed, then the worst thing that'll happen is a stall. But when you're faster than maneuver speed, we could have structural damage. We could bend metal, literally bend the wings, have structural damage or structural failure. So the best answer choice here is speed of the airplane. If you're traveling extra fast, then you are exposing the possibility of having extra load factor imposed upon your airplane. All right, we have more aerodynamics questions. Induced drag. Induced drag increases with an increase in angle of attack. So if we hold our nose up and we increase our angle of attack, we are increasing induced drag. Induced drag is going to be most apparent at high power settings, low air speeds, high angles of attack. Think about that wake turbulence, those wingtip vortices. Aerodynamics. All right, so here's a great figure question. Figure 25, which airport is fixed wing, special VFR, not authorized? So we said that we can do the search feature for figure 25. So we hit Control F, figure 25. Maybe we need to rotate it. Oh, here it is. Perfect. Figure 25. So what you're really all paying attention to, I'm going to hit Control plus, see if I can zoom it in. Or I think here we go. We're studying this airport right here. It says Dallas Fort Worth International. Their control tower frequency is 124.15. I'd like to zoom it in more, but I don't know if it's working. There it goes. Control tower frequency is 124.15. They also have another control tower frequency of 26.55 and another frequency of 27.50. And then also 34.9. So there's multiple control tower frequencies at this airport, one of the busiest airports in the country. ATIS, remember that's once an hour updated information on 123.775. In your actual radio, you just dial 77. The last 5 is implied. Remember, 607 is the field elevation. L means lighting, so the airport is lighted. It is not pilot-controlled lighting. Star L is pilot-controlled lighting. Longest runway is 13,400 feet. The Unicom is 122.95. AOE, airport of entry. So we're always trying to practice up on reading our airport data blocks. That's really fundamental information for everybody. And then at the top, here's the key words for this question. NO SVFR, no special VFR. You see the same thing very similar over here at this other airport nearby. So when an airport says no SVFR, then that means that airport does not authorize, does not give special VFR clearances. Remember, special VFR, 1 statute mile clear of clouds. That's regulation 91. 155 tells us the normal VFR cloud clearance visibility requirements. Special VFR would be, what is special VFR? It's when a control towered airport lets you operate using the uncontrolled minimums. So this airspace here is a Bravo airspace. Bravo airspace typically would be 3 miles visibility, clear clouds. It's a control towered airport. So at control towered airports, they possibly might give you a special VFR clearance if you request it. Bad idea, I wouldn't recommend it. And that authorizes a pilot to operate with less than prescribed minimums. But the special VFR minimum requirements are 1 mile clear clouds. So we're going to see a lot more questions about those VFR cloud clearance visibility requirement minimums. And there's a good review for you to get your brain warmed up. And at Dallas Fort Worth International and Dallas Love Field, we pointed both of those out to you. They do not authorize special VFR for us fixed wing pilots. All right, well, looks like we're on the same figure 25. This time we're looking at area 2. We want to know what is the control tower frequency for Addison Airport. So here's area 2 underneath my mouse, and here's Addison Airport. It tells us the control tower frequency, CT, is 126.0. So the control tower is 126.0. It then says star. The star means part-time tower. There's a C in a circle. So when tower goes to bed after hours, it turns into an uncontrolled airport, and C in a circle is for CTAF frequency. The same 126.0 frequency would be used for your CTAF, Common Traffic Advisory. This airport, field elevation 645, we see star L. Remember that star L, lighting limitations exist. Typically, pilot controlled lighting, where we push the talk button to get the pilot controlled lighting to turn on the runway lights. This airport is a delta airspace. Remember your delta airspace because we have a dashed blue. In this case, the dashed blue, the delta airspace goes up 3,000 MSL. 3,000 MSL. Typically, you see a delta airspace rise 2,500 AGL, which makes sense. Looks like our field elevation here at this airport, 487, which is very similar to 500 feet. At this airport, they have a very tricky little minus sign. There's a minus sign for that 30. So technically, the delta airspace does not include 3,000 MSL. So your delta airspace goes up to 2,999 MSL. And then at 3,000 MSL, we're no longer delta. At that point, we're probably looking at Bravo. Remember, your Bravo airspace is the solid blue. So airspace is a huge fundamental, and we are learning, we are practicing, we're reviewing how to find some of that information off of your sectional chart. Control tower frequency for Addison Airport. Here's some more questions about sectional chart. And unfortunately, I've seen several tests where we have students missing this question here. So what is true concerning the blue and magenta colors used to depict the sectional, to depict the airports on the sectional aeronautical chart? So the correct answer is that airports with control towers underlying Bravo, Charlie, Delta, and Echo airspace are shown in blue. So that sounds kind of tricky. Let's make it a really simple statement. Airports that have a control tower are shown in blue. Blue airports have a control tower. Magenta airports are uncontrolled and they do not have a control tower. So this is an exercise of studying the legend. This information is actually already posted on the chart legend. And I want to show you something about this. So when you take the written exam, you will see it'll tell you to reference a figure, but the written exam will not tell you to reference a legend. So if I can get my PDF document to load up, you can go to the front of your supplement book. Unfortunately, it doesn't respond very quickly. There we go. Might need to zoom out too. Might need to scroll down a few. We can look at the beginning of this document to find legends. So when you're taking the written exam, say that question was troubling you, you could find the legend that shows a sectional legend, and I can show you, just like we did in class before, how to find that. So here, Appendix 1, legend, sectional aeronautical chart. So that's legend. And here's the answer. Airports having control towers are shown in blue. All others are magenta. I know that's really small. I could try to zoom in if it works for us. There you go. Airports having control towers are shown in blue. All others are magenta. And this document here, the legend, could be very helpful to you because you might be taking that written exam. I had students missing questions on our test over some things such as, what's the control tower frequency? Well, you can open up this legend and it'll point it out to you right here and explain to you everything in that airport data block. Yes, we should already know how to read the legend and know what the symbology means, but in a pinch, you could literally open up this document and see how is Class Bravo airspace depicted? How is Charlie airspace depicted versus Delta? What does it mean if there's a CT 118.3? Well, CT means control tower, primary frequency. So this legend is one of the most important things that we need to study. All right, so I'll get off my soapbox and we'll keep moving. Here comes an aerodynamics question. In straight and level flight, if thrust exceeds drag, then speed increases. So remember your four forces: lift, weight, thrust, and drag. So in steady state, unaccelerated equilibrium, the opposing forces are equal. They are balanced. Well, in this example, we have straight and level, but wait a minute, we are not unaccelerated. Thrust exceeds drag, so we are accelerating. We are speeding up. So that's answer choice A, the speed is increasing. More aerodynamics. Yay, aerodynamics. We're so excited for it today. Skin friction drag. Okay, skin friction drag can be somewhat reduced. Flush riveting, smooth paint, and waxing. So extra credit if you get out there and wax the airplane before I hop in. I like it when we go a little extra fast. Awesome. So what kind of drag are we talking about? We're talking about parasite drag. So remember, parasite drag increases at the square of velocity. Whoa. So if we double our speed, we actually quadruple our parasite drag. And review from our aerodynamics section, parasite drag would be things such as rivets, any sort of dirt. So we can reduce that by having flush rivets, smooth paint, and waxing. You'll often see that airplanes involved in speed races will have all those. All right, here's a good question about high density altitude. So what effect does high density altitude have, as compared to low density altitude, on propeller efficiency, and why? So remember, what does high density altitude mean? It means the air is really thin. The air is less dense, very thin, less dense air, like you're at a high altitude, high density altitude. Think about being in Colorado on top of the mountain in the middle of summer. It's very thin air, hot. Your engine is not going to perform well. You as a human being are not going to perform well. You try to run a mile on top of the mountain in the summer, there's not as much air molecules to have a good breath. The partial pressure of air is less. And it's way different than trying to go run a mile at sea level. I haven't ran a mile in a long time. I would struggle regardless. But if you're on top of the mountain in the summer, it would be extra difficult because the air is thin. So that's what's going on with our engine and our propeller. So what's up with propeller efficiency? Efficiency is reduced with high density altitude because the propeller exerts less force at high density altitudes than the low density altitudes. Why is your propeller exerting less force? Well, think of it like a shovel. It's shoveling or paddling air backwards, but the air is way more thin. The air is less dense. So if every shovel load backwards is a smaller amount of air, then you're not going to have as great of propeller efficiency. And this is one of the reasons why propeller airplanes don't fly at super high altitudes. It's always the jet that flies at super high altitudes. High density altitude. We'll be talking a lot about that with our next section with weather. All right, here's a question that I'm getting some feedback on. I've had some emails. Thank you guys for sending me emails and giving me feedback. This question here is going to reference a figure 36. We'll open that up and look at it in a moment. It's telling us, this question, that we have a reported wind of south. That's 180. We have a wind from south at 20 knots. Which runway should we use? Runway 10, runway 14, runway 24? Which runway is appropriate for an airplane with a 13-knot maximum crosswind component? Interesting question. Remember, these are timed tests. So when you go to take the real FAA exam, there is a time limit. and you want to think about 3 types of questions that you can encounter. You can encounter 3 types of questions when you take the written exam. A question you immediately know the answer to, just click it, move on. A question that you think you know the answer to, but you might have to do some math, you might need to open a figure, go ahead and skip it, move on, mark it. And then a question that you look at and you say, ooh, this is a doozy of a question, very difficult, lots of math, lots of figures. You might want to skip it and save it for the end. So the idea is that you don't want to burn yourself out. You want to try to eliminate those difficult, time-consuming questions and come back to them later on in your test taking. This question here, yes, there is a figure. Yes, we can open the figure. I will open it and show you how to determine the answer, but I'm explaining to you that you can figure out the answer to this question without ever even needing to open the figure. So let's really analyze it quickly. The wind is from the south. That's 180. Sure, the wind's blowing at 20 knots. Okay, sure, the airplane has a 13 maximum crosswind component. The question is still simply enough, how do we choose the best runway? We want the most amount of headwind. We want the least amount of crosswind. So if I choose runway 10, that's 10. If I was to land my airplane on runway 10, when my nose points down final to land, I would be pointing in the direction of 100 on the heading indicator, on the magnetic compass, on the HSI. So when I fly that magnetic course of 100 and the wind is from direction 180, well, that's math. 180 subtract 100. That is an 80-degree angle difference. 80-degree angle difference. Well, if you had 90-degree angle difference, that's a straight crosswind. Directly 90 degrees off your nose is a straight crosswind. So if you choose runway 10 and the wind is from 180, that is an 80-degree angle difference. That's a lot of crosswind. Don't even have to look at the chart. That's almost a direct crosswind. So I'm thinking that runway 10 may not be the best choice. Let's analyze the next option. 14, runway 14. Well, if you're coming down final 140 on your magnetic compass and the wind is blowing from 180, that is a 40-degree angle difference. A 40-degree angle. Well, that's much better. That's a much better choice. If the wind is only 40 degrees off of my nose, that is less crosswind. If it was perfect headwind, it would be 0 degrees off my nose. Straight down my nose would be perfect headwind. If I land on runway 14, my crosswind is only 40 degrees off my nose. That answer choice looks pretty good compared to our first answer choice. What's our last answer choice? Runway 24. So that means if I come down final, I am pointing in the magnetic direction of 240. If the wind's from 180, well, that's a 60-degree angle. 60. So we have to choose which one of these runways gives me the least amount of crosswind. Which one of these runways gives me the most amount of headwind? Well, the answer is runway 14. Because 14 to 18, 140, the difference of 180 is only 40. That's the smallest angle difference. That's the least amount of crosswind, the most amount of headwind. So that's why the correct answer choice is actually runway 14. With that said, I'm going to open up the figure and walk you through how you could do this problem and spend extra time on it, but you might not want to on the day of the written exam when you're at the timed test. We're looking for figure 36. So we type Control F, figure 36. We need to rotate. Here's a nice looking rotated crosswind component chart. Whenever you're working on charts, whenever you're working on figures, these are kind of like performance charts, figures, typically you're gonna find an example. So in this case, there's an example right here on the chart. So if you ever get a question that you don't understand chart-wise, you can follow the example And that can help you to apply, plug and play the new numbers for your particular problem. For today, I'm just going to walk you through our problem that we just discussed. We said that we think we should land on runway 14. We know that the wind is from 180. So that is a 40 angle difference. So right here is 40 degrees, and that is going to be the angle difference between the wind and the runway. Over here on the y-axis, where my mouse is, you can see this is where the headwind component. If I scroll down a touch more, down here you can see crosswind component. So wherever we find our mouse pointer at, wherever we find our plot, and we figure out the difference of the angle of the runway and the wind, and we figure out how strong the wind is, when we move to the left, we'll see how much headwind that could be. We'll move down, we'll see how much crosswind component that would be. In our example, we said 40 angle difference between the runway center line and the wind from 180 and 140. That's a 40 angle. We said the wind was reported as 20 knots. So here's 20, and there's an arc, and here's 20. So we're 40 angle, and we plant right here where my mouse is. Oh, sorry. There you go. I plant right here where my mouse is. 20 arc. I'm on the 40 angle difference between center line and wind, and 20 wind arc. If I read straight down, it'll tell me what the crosswind component is. If I read straight left, it'll tell me what the headwind component is. So this question is asking about crosswind component. So if I move my mouse straight down, it looks like I'm at about 13 degrees, 13 knots, 13 knots of crosswind. Whereas if I would have moved straight to the left, I would have found about 16 knots of headwind. The question says my airplane has a maximum crosswind component of 13 knots, and using this problem here, 40 angles straight down, I get about 13 knots of crosswind component for that particular example. If we was to run any of the other answer choices, we would find greater amounts of crosswind. But then, like I explained to you, you don't even have to pull the chart to be able to try to figure out what is the correct answer. So crosswind component chart, it's a really good tool. You should know how to work it, yes. But there are not a lot of pilots when they're flying airplanes in the real world that are going to pull out a crosswind component chart and do that extra math. They're just going to try to do some quick round numbers to figure out where is the least amount of crosswind, because we as pilots want to land with the most headwind and the least amount of crosswind. With that said, when you're out flying airplanes with your instructor, when you have the opportunity to practice crosswind landings, do it. That is some of the best experience you can get with your instructor. When you have the opportunity with your instructor, say, yes, I want to go practice more crosswind landings. There will come a day when you fly an airplane by yourself and you have to land some crosswinds, and you're going to want to have had that extra crosswind landing experience. A little more difficult, a little more tricky. Okay, whew, a lot of information. We're back to humidity. We're talking about density, altitude, humidity. So the whole idea about performance is that there are three variables. There are three variables that influence density, altitude: temperature, pressure, moisture. This is going to tie into our next chapter as we get into weather. There are three elements that tie into density, altitude: temperature, pressure, and moisture. In this case, we have high humidity. That means high moisture. So if we have high moisture, that is less space for air molecules. So the air is less dense, and we don't have as good a performance. Every time you take a breath in, you're getting less air molecules. Your engine is getting less air molecules. Your propeller moves less air molecules. So what effect does high humidity have on performance? It decreases performance. All right. Here's a VASI, V-A-S-I, Visual Approach Slope Indicator. It's a repeated question we saw from one of our previous tests. A VASI provides visual descent information to the runway. So Answer choice B is incorrect because it says left and right guidance. Negative. Your VASI, visual approach slope indicator, is more up and down, vertical guidance. Answer choice C is wrong because it does not light up the runway. No, it is the red and white lights next to the runway that help you determine your glide path to approach the runway. Remember, a 3-degree glide path is optimal. You are on the ground and you see a steady red light signal from the tower. What does this indicate? So this is from our chapter 5, the ATC light gun signals. Steady red, you stop. If you're on the ground and you see a steady red, you stop. ATC light gun signals. All right, you see a runway hold position marking on the taxiway. What does this marking indicate? Holds aircraft short of the runway. So you're on the taxiway, you see the hold short line, that means you're about to leave the taxiway and get onto the runway. So you'd be a double solid, double dash, and you stop on the double solid side. Do not cross the double solid lines unless you have permission from ATC. If it's an untowered airport, you need to at least make a radio call and make sure it's clear before you cross that hold short line. All right, here is from chapter 2 question, our flight instruments. Figure 4, which color identifies the power off stalling speed in a specified configuration? So we're looking for power off stalling speed, figure 4. Oh yeah, look at this good looking airspeed indicator. So here's a nice good looking airspeed indicator. On this airspeed indicator, we are studying the green arc. Remember, the green arc is our normal operating range. The lower limit of the green arc would be where the airplane stops flying and the airplane stalls, you're too slow. So that would be called VS, stall speed, in a clean configuration. That's the bottom of the green arc. Whereas the top of the green arc, where it meets the green and the yellow, that's VNO, maximum structural cruising speed. I think a lot of students are getting confused on this question because it says the lower limit of the green arc. So this, where my mouse is the lower limit. I could see why some students think it's the upper limit, but negative, this is the lower limit. The lower valued numbers here, the lower limit. So the power off stall speed of this airplane is probably about 57 knots or so in a clean configuration, the green arc. That's different than the wide arc. The lower limit of the wide arc would be your stall in a landing configuration, in a dirty configuration with the flaps and gear extended. Remember, top of the wide arc would be the maximum flap extension speed. And remember the red radial line, VNO. Dang it, I said it wrong. VNE, never exceed speed. So this question in particular is asking about the green arc. The lower limit of the green arc is the stall speed in a clean configuration. So when we check our question and answer, what color identifies the power off stalling speed in a specified configuration, lower limit of the green arc? Both of the other answer choices say upper limit. Upper limit of the wide arc, as we discussed, is the maximum flap extension speed. Upper limit of the green arc, as we discussed, is the VNO, which would be your maximum structural cruising speed. And so you can go faster than the top of the green arc, but only if it's smooth air. And usually you're getting faster than maneuver speed at that point. All right, we're tying it all together. We're gonna answer a few more questions here before we go on our break. So here is the figure is already printed on this question. That's nice. We need to know the difference between area A, alpha, and area E, echo. Alpha is the arrows. We cannot land on arrows, but we could use the arrows to back taxi, take off. So we can drive on the arrows, we can taxi on the arrows, but we cannot land on the arrows. versus area echo, E. Those are chevrons. We are not supposed to taxi, land, touch chevrons. The only purpose of the chevrons is in the event of an emergency, an overrun type of area. Sometimes those chevrons don't even have full strength concrete. Remember EMAS, emergency material arresting system, they mix styrofoam in with the concrete, and so it would collapse under the weight of a large airliner. So the answer choice A may be used for taxi and takeoff. Echo may be used only as an overrun. So only in an emergency would you ever let your aircraft wheels get onto the chevrons. But A, the arrows, yes, we could use that for takeoff. We could use that for taxi. All right, we got ourselves another figure question. Figure 50, 50. Which runway and traffic pattern should be used as indicated by the wind cone in the segmented circle? So we're going to check out answer choice number 50, and we need to know, are we going to do left-hand traffic? Are we going to do right-hand traffic? Are we going to use runway 36, 18, 9? What's going to be the correct answer? The suspense is killing us. Maybe so, maybe not. Okay, look at this nice looking figure here. We got a windsock and a segmented circle. What's happening is that we are seeing the wind blow, and so the wind is blowing from the northwest, and it catches the larger mouth end of the windsock, and then the smaller tail end of the windsock will stand up as the wind blows. So in this example, we are seeing the wind blow from the northwest. We like the idea of taking off with a headwind, not so much of a tailwind, not so much of a crosswind. So in this example, it looks as if we could choose to take off to the north on this northern runway. See our segmented circle, the white markings? So if we take off to the north using runway 36, when we take off, when we land, when we use runway 36, when we point our nose to the north, we would be pointing northerly in this direction. And then after upwind, we would turn left, as indicated by this segment circle, for left crosswind, left downwind. And as we go left downwind, we'd make a left-hand turn for left base, and then left final. So we could imagine using left traffic for runway 36. In this example, it could also be a choice to maybe possibly point our nose to the west. So here, if you watch my mouse, my nose is dragging from the east to the west, and my mouse is traveling west. So if we was to use runway 27 and point our nose to the west, 270, you would take off pointing west. The segmented circle shows we would make a right-hand turn for right crosswind, a right-hand turn for right downwind, a right-hand turn for base, right-hand turn for final. So using this figure, we see that the wind is from the northwest. That's either going to be a left-hand traffic pattern for runway 36, or it could be a right-hand traffic pattern for runway 27. I can imagine either of those answers working out. So I go check my test, and runway 27 is not even an option. So the best answer choice is our left-hand traffic for runway 36. If you chose right-hand traffic for 18, you would have a tailwind. If you choose right-hand traffic for 19, then you're not reading the segmented circle correctly. Because if you take off in an easterly direction, 090, the segmented circle shows that it's a left-hand turn, a left-hand traffic when you point the nose 090, regardless of the fact that'd be a tailwind. Cool. Let's try to get through a few more and then we'll take a break. This one's a real important question for us here. Crosswind correction. So the figure is already printed for us. That's nice. How should the flight controls be held while taxiing a tricycle geared equipped airplane into a left quartering headwind? Cool. So they're showing us this A arrow. We're saying that we have a left quartering headwind. So the idea is that the pilot wants to avoid that wind from getting underneath the aileron to lift up and try to flip the airplane over. So the idea is that if you were flying the airplane, I'm going to switch off of the screen share for a minute. Okay, so I think you guys see my face here. So when you fly airplanes that have a yoke, I know we have a side stick, we have a stick in the Cirrus, but a lot of the Cessna and Piper airplanes, they actually have a physical yoke. And so I kind of like hold this shape up, and you know this might be like a yoke. You know, if you twist the yoke in one direction or twist it the other direction. And I'm facing you head on right now, so I gotta maybe like imagine like if I was facing here with you like this, and we're flying the airplane. Awesome. Feels good to be in the pilot seat, right? Yeah, flying the airplane. Okay, so if we have a headwind, imagine that this yoke is like a bucket. This yoke is like a bucket. And so if I have a wind coming headwind, left quartering headwind, I'm going to twist my yoke this direction. And that's going to allow me to catch the wind in my bucket for like a headwind, for a takeoff. This is the proper crosswind correction if I have a headwind. If I'm trying to land or take off, you twist the bucket to catch all the wind because the wind's coming forward from my left. I'm trying to catch all that wind in my bucket. That is different than if you're back taxi. That is different than if you are doing a tailwind. Like if you back taxi for a tailwind, if I had a back taxi tailwind, say the wind's coming off my back left shoulder, the wind's coming from my back left shoulder, then I do not want to catch any wind in my bucket, and I turn my bucket the opposite direction. So this bucket scenario is something that really helped me out a lot when I was learning to fly airplanes. And this is just another chance for us to get to apply that information. So if we study the diagram, we see that we have a left quartering headwind. So I'm going to twist my bucket, my yoke, to the left, and I want to catch all that wind in my bucket possible. When I twist my yoke left, that's going to be raising the left aileron. That would be dropping the right aileron. So, you know, this is like a flight controls question from our flight controls chapter. And so with answer choice A, you would want to twist your yoke to the left, and that would raise your left aileron and drop your right aileron, which is why we get answer choice A here of left aileron up, elevator neutral, to be our most correct answer choice. Goodness. Cool. So at this point, I'm going to hit stop share. And we're probably about to take our break. Nobody has to, if anybody has to use the bathroom, whatever you got to do. Is there any general questions before we break? Good, bad, ugly? Feedback?
Good review so far.
Hey, I appreciate the feedback. Thank you so much. Okay, so we're going to take 10 minutes. We'll be back in 10 minutes. And thank you so much. So it looks like Charles made it in after all. So we got Charles there, so I'll change that in the grade book. So how you guys feeling? Good, bad, ugly? Everyone's had a chance to use the bathroom, chew a bite of food.
Good so far.
Awesome. Thank you for the feedback.
Yeah, can't complain. Everything's going pretty well.
Awesome, awesome, cool. Well, I guess I'll keep trucking here. I mean, do you guys think this is helpful? You feel like this is a waste of time? You think this is good?
I mean, I think it's helpful, but definitely there's some questions that, if we're, in my eyes, if we're not given any feedback, we probably don't understand it pretty well. Or, if you explain it well enough, most people probably won't have any questions, because that's how I tend to look at it. I don't know how everybody else is, but.
No, I appreciate it. Thank you. Yeah.
Yeah, usually with me, like once I see that I have something wrong and tell myself what the right thing is, it kind of works its way in there.
And that's really what's so important about these like practice writtens. Remember, like every chapter you're seeing that you need to go complete a new practice written, because when you take a practice written and you miss questions, then it's going to expose you to that information and make you have to suddenly realize that, there are some questions out there you probably haven't seen yet. Because together as a class, we're just not physically going to be able to cover every single possible question that's on that written exam. You're going to have to take a lot of practice writtens to get to expose all those questions. Cool. Well, I'll click the button to share the screen. We'll keep on trucking here. I'll try to move a little bit faster with you. I saw multiple people missing this question. After takeoff, which airspeed would the pilot use to gain the most altitude in a period of given time? So that's VY. Why is it VY? Because the word time. So the most amount of altitude per unit of time, VY. Vx, that would be the most amount of altitude per given unit of distance. So Vy, best rate of climb. Rate implies time, most altitude in a period of time. Vy, that's the correct answer, because most altitude given period of time. If the question would have said best angle climb, most altitude per unit of forward distance, that'd be Vx. That'd be like your short field takeoff. VA, that's maneuver speed, at or below maneuver speed. Worst that'll happen is a stall. If you're faster than maneuver speed, you have structural damage. Okay, here's a weight and balance. An airplane has been loaded in such a manner that the center of gravity is located aft of the limits. So our CG is too far back. We got too many heavy people in the back seat. One undesirable flight characteristic a pilot might experience would be difficulty in recovering from the stalled condition. So that's the best answer choice. Remember, CG, center of gravity, all motions occur about the center of gravity. In this case, we're talking about our ability to get the nose down. So if the airplane stalls and we exceed the critical angle of attack and the nose is too high, we must get the nose down if we want to get back to good flying. So we're going to do that by pushing the tail up. We're a teeter-totter, push the tail up, brings the nose down. So it's the effectiveness of the elevator. The effectiveness of the elevator. If I have an aft center of gravity, it is a very short arm lever between the CG and the tail section. So our elevator is not as effective with an aft center of gravity. B is a bad choice. A longer takeoff roll, that would be if you had a forward center of gravity. Stalling at a higher than normal airspeed, that would be a forward center of gravity. All right, and then 25, an airplane said to be inherently stable will require less effort to control. It's just an FAA question. I know they all seem like good answer choices. You just got to memorize. Require less effort to control. Airplane said to be inherently stable. That's the best answer choice according to the FAA today. All right, at what altitude should the altimeter be set to 2 when you're climbing to a cruise flight level? So they're talking about flying in alpha airspace, A airspace. When you fly through 18,000 or flight level 180, that is where all the pilots change from local altimeter setting to standard pressure altitude 2 So the correct answer choice here is 18,000 MSL. And I do have a few of y'all missing this question. So 18,000 MSL. Flight level 180. Okay, here's a airspace question. Flying through a restricted area should not be accomplished unless the pilot has received prior authorization from the controlling agency. Restricted area, it's off limits unless ATC says you're allowed in it, unless ATC says that it's not active, not hot. Okay, we are doing a figure 25, area 2, the floor of the Bravo airspace at Air Park, Dallas. That's Fox 69 Airport. The floor of the Bravo airspace, area 2. We're on figure 25. So we're clicking figure 25. We're going to give it the rotate. There it is. And we're looking at figure 25, Air Park, Dallas. You see the magenta data block? Air Park, Dallas. I think that's what we said. So the floor of Bravo airspace at Air Park, Dallas, Fox 69. Oh my goodness. That's not what I want. Okay, so Air Park, Dallas. We need to find this airport called Air Park, Dallas. Here it is. So it's a magenta data block for a magenta airport. So here's the magenta airport. This one's a little tricky because our magenta uncontrolled airport actually falls within controlled airspace. So you have the blue Delta airspace for Dallas Love. I said that wrong. That's down here. Addison. So here it is. Addison. So Addison blue is this airport Delta. And then magenta is our uncontrolled airport, Air Park, Dallas. So you do not need clearance to land or take off from Air Park, Dallas, but you would need to contact Addison Tower when you enter that airspace for landing. The question is, where does the Bravo airspace begin above Air Park, Dallas? So the answer is right here. So this shelf of the Bravo, I'm outlining the shelf of the Bravo with my mouse pointer. I'm outlining the shelf of the Bravo with my mouse pointer. It's showing us that the floor is 3,000 MSL and the ceiling is 11,000 MSL. So above Air Park, Dallas, it is 3,000 MSL, and that's where the Bravo airspace begins. So remember that exercise where you practice going straight up in a jetpack, 1 foot off the ground and up? That's an exercise you should practice for, lots and lots of airspace examples to get you through your check ride. So here, once you're 1 foot off the ground, we're in Delta airspace. A Delta airspace goes up to 3,000, not quite 3,000, 2,999 MSL. And then we're in the Bravo airspace from 3,000 MSL to 11,000 MSL. Above 11,000, we're in Echo, and the Echo goes all the way up till flight level 180, 18,000. Alpha airspace up to 60,000, flight level 600, and then we're back into Echo again. So there you go, tricky airspace example, and we discovered that the Bravo is 3,000. The floor of the Bravo on that shelf is 3,000 MSL. All right, airspace at an airport with a part-time control tower is classified as Delta only when the control tower is in operation. If tower goes to bed at night, then it's no longer a control zone, and they're not going to be able to give you any sort of clearances to enter, or you won't have to establish communication to enter if there's no control tower active. So part-time tower means that it's part-time Delta airspace. So Delta Airspace only when the control tower is in operation. All right, so in our next question, we want to operate Echo Airspace at night. Well, this is a famous airspace 91-155 regulation. Echo Airspace at night, 3 miles visibility, 1,000 feet above, 500 feet below, and 2,000 foot horizontal from every cloud. All right, we'll keep moving. We've covered that one a few times. Figure 23. We want to know what the floor of the Savannah Charlie airspace at the outer shelf, at the shelf area, the outer circle. So just looking at the answers, we know answer choice C is probably not going to be correct because that's an AGL number, above ground level. Us as pilots, we just want to look at our altimeter, look at the sectional chart, and not have to do any extra math. So the sectional chart is going to predominantly for Charlie airspace, it's going to be depicting MSL altitudes. So we have to debate between 1,300 and 1,700, figure 23, area 3, Savannah, Charlie C, figure 23. Let's go 2 pages up. Maybe. I guess I'll do Control F then. Oh, there it goes. Figure 24, a few more pages. Oh, there's Savannah Charlie. Savannah. Gosh, we got to rotate it. The old flip-flop. One more. All right, we're rotated. Oh yeah, look at this nice looking sectional chart. So when we study Savannah Airport, here's the city of Savannah. Here's the airport data block. It's in blue because it's a control towered airport, like a blue airport, remember that? Savannah, Hilton Head, and here's all the information. We've covered that multiple times. Let's focus on the airspace. The outer shelf versus the inner core. So our outer shelf is showing that the floor of the Charlie, 1,300 MSL, to the ceiling, 4,100 MSL. So there you go. That's what's going on here with Savannah Charlie outer shelf. 1,300 MSL is the floor, 4,100 MSL is the ceiling. Hey, while we're here, how about a few other fancy airspace questions for you? What would be the maximum airspeed in an outer shelf? That would be 250 knots indicated. Whereas if you was on the inner core of a Charlie, your maximum airspeed would be 200 knots if you were in 4 nautical miles of the core. How about transponder operations? Sometimes, people ask the question, do you need a transponder to overfly Charlie? Yeah. Do you need a transponder to go under the shelf? Not so much. So we're asking airspace questions and we're reviewing how to read the sectional chart. So that's why your answer choice here is 1,300 MSL. Okay. Pilots that fly over National Wildlife Refuge requested to fly no lower than 2,000 AGL. That's a single solid blue line with blue dots on the inside. Wildlife Refuge. You are requested to fly no lower than 2,000 AGL. All right, here's a chapter 2 question for you. Internal cooling. A reciprocating aircraft engine is especially dependent on the circulation of lubricating oil. That is the correct answer. So answer choice B is a distractor. We don't have that. We have a air-cooled engine, so we don't really have a thermostat per se. Answer choice C is a distractor because it says air flowing over the exhaust manifold. So the exhaust is going to be really hot, and throwing air over it, could help cool it down. But we're trying to talk about internal cooling, so the actual inside of the engine. So lubricating oil is the best answer here. How can you determine if another aircraft is on a collision course with your aircraft? I have a few of you all missing this question, and I feel like we even covered it, during our review session last time. But the answer is there is no apparent relative motion between your aircraft and the other. So I have a lot of you guys choosing the answer choice C. I mean, I don't disagree. Gosh, if you see an airplane getting larger and larger in your windscreen, it's a bad deal. But if it's really getting that larger at such a rapid rate, you'd hate to think it's too late. So the bigger thing that you need to be watching for is answer choice A. There is no apparent relative motion between you and the other aircraft. So if that aircraft seems to wander left, wander right, wander up, wander down, that is relative motion. But if you see that same dot on the windscreen and it doesn't move and it stays in the exact same spot, chances are it could be on a collision course with you. All right, here's a chapter 2 question. We have a pitot tube and outside static port, outside static vent. If they both become clogged, what instruments would be affected? So we need to know what instruments are connected to the static port. The altimeter, the airspeed indicator, the vertical speed indicator. These are the pitot-static instruments. They're all static instruments. They all connect to the static port. The altimeter, the airspeed, and the vertical speed. They all connect to the static port. So the outside static vent becomes clogged. Those are affected. This question adds in the pitot tube. The pitot tube is only connected to the airspeed indicator. The airspeed indicator connects to both the pitot tube and the static port. So this is your best answer choice. B is wrong because it says turn and slip indicator. It says attitude indicator. Well, those are gyroscopic instruments, if you remember. So answer choice A. Yep. All right, look at this nice question here. Remember our turning tendencies? We have turning tendencies. In what flight condition is torque effect the greatest in a single engine airplane? Low airspeed, high power setting, high angle of attack. So we talked about that earlier. This is the same setup for the worst wingtip vortices. It's the same setup for the most amount of induced drag. It's the same setup for the biggest amount of left turning tendencies, or turning tendencies for our aircraft. So low airspeed, high power, high angle of attack, that's where we're going to have the most amount of torque. For every action, there's an equal opposite reaction, torque. All right, look at this good question. Night flight. So we talked about this one in our review session as well. During a night flight, you observe a steady red light and a flashing red light. So the steady red light is the wingtip light. So the other aircraft that you're observing that's flying in front of you, you're seeing the steady red left wingtip. And then you're seeing the flashing red, which would be their beacon on their tail. So you observe this steady red light and flashing red light ahead at your same altitude. What is the general direction of movement of that other aircraft? The other aircraft is crossing to the left. The other aircraft is moving from the right to the left. And that's why you see their left steady red wingtip and also their tail anti-beacon light system, which is a flashing red in this case. Answer choice C, if the aircraft was crossing to the right, from your left to your right, you would see more of the green steady light, not the red. How can you remember this? I feel like I've heard people talk about how your heart is on your left side of your body. So your red nav light, your red nighttime wingtip light is on the left side of the aircraft. Okay, you are inbound to an airport that doesn't have a control tower, flight service station, or Unicom. Gosh, what do they have? So the pilot should self-announce on a multicom frequency, and that's 122.9. This is just one of those tricky questions. We pointed out in the book, we pointed out. So just you need to know for the written exam that if there's no other general frequency to use, the answer is supposed to be multicom, and multicom standard frequency is 122.9. I put this question on here because it's kind of tricky. It's not something we use every day in the flying world, so it's good to keep that piece of information in front of you in preparation for the written exam. Oh, we got a good figure question. We're going to be checking out Dallas Executive Tower, but the tower is not in operation, so it sounds like it's a Delta airspace, and the tower went to bed at night. They're saying, what frequency should we use as the CTAF, Common Traffic Advisory frequency, if we want to monitor, listen to, communicate with the airport traffic pattern? So we're going to check out Figure 25, Area 3. We're looking for Dallas Executive. Figure 25. Should be able to just go down a few. I don't know if it's faster to hit Control F or not. So what I'm thinking we're going to find is that Dallas Executive is probably a Delta airspace. A Delta airspace is going to be a dashed blue. And we got to give it the rotate. Delta airspace is going to be dashed blue. Here it is. There she be, the airspace in question, Dallas Executive. Let's see if we can zoom in once and get even a closer look at it. So Dallas Executive, it looks like its identifier is Romeo Bravo Delta. It says Area 3. It's that Delta airspace we talked about. There's your Delta, blue airport control tower. And they're saying the control tower frequency is 127.25. But wait a minute, there's a star, part-time operation, tower goes to bed at night. So we got a C in a circle for common traffic advisory frequency. So when tower goes to bed, 27.25, there's C in the circle. That same exact frequency is what you would use for your common traffic advisory calls. So that's why we think that the best answer choice is going to be 27.25. 127.25. All right, we're going to keep moving. This is a Chapter 5 question, radio communications. There's an aircraft called Hawk 666 Charlie Bravo, and the proper phraseology for initial contact with McAllister AFSS, that'd be your flight service station. It's called McAllister Radio, Hawk 666 Charlie Bravo. I'm receiving over the Ardmore Vortac, over. So it's a little bit of a history lesson that flight service station, originally you call them radio. So I know like when you go to Canada and you fly around there, they actually still have radio operators at all the airports. I'm not trying to confuse you with different countries' airspaces operations, but there's kind of a bit of a history lesson there and how they're doing it and how we used to do it. But the idea is that when you say the word radio, you want to talk to a person named Radio. That means you're trying to talk to a person called flight service. In the real world nowadays, you can say radio, you can say McAllister Radio, you can say McAllister Flight Service Station, flight service, whatever you call them, they'll probably respond and answer to you. But to pass the written exam, the more correct answer is that it's called McAllister Radio. And then you, as the pilot, are saying your tail number, which is Hawk 666 Charlie Bravo, probably a Skyhawk. And then you are receiving over the Ardmore Vortac. So remember we talked about RCO, remote communications outlet, repeater towers. So you are going to receive their transmissions over top of the VOR in this case. And then over is a little bit of a history lesson. You know, when you got done saying a radio call, you would say over to let them know that's the end of your radio call. We don't really do that a whole lot nowadays when we speak on the radio, but in this example, for the written exam, that's what they're using. All right. Yeah, I mean, you can see that answer choice B is not the best because it says CB. So you need to know your phonetic alphabet, Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf. You need to know all those, and C is Charlie, B is Bravo. So that's not the correct answer. And then here, in answer choice C, it's not so good because it's saying November 6, Charlie Bravo. So this pilot in answer choice C is not using their full tail number, their full call sign. So that's why answer choice A is our best. All right, here's a good aerodynamics question. We love aerodynamics. Hooray, aerodynamics. In what flight condition must an aircraft be placed in order to spin? The answer is A, stalled. So what is a spin? It's an uncoordinated stall that results in auto-rotation. So the idea is that we must be in a stalled condition to ever see the airplane spin. So answer choice A, stalled. Why is B not the answer? Because it says partially stalled with one wing low. You can stall an airplane with one wing low and it doesn't mean the airplane is going to spin. If you haven't done turning stalls with your flight instructor, then next time you go fly the airplane with your instructor, say, hey, instructor, I would like to do some turning stalls today. So you should practice turning stalls. And if you keep the airplane coordinated, even if you stall it during a turn, you're not going to spin the airplane. C is not the best answer choice because it says a diving spiral. So you're learning the difference between spin and spiral. A spin is when we are in a stalled condition, uncoordinated stall resulting in auto rotation. A spiral implies that we have airspeed. So in a spiral, there's way more load factor because you're at a way faster airspeed. Think about unusual attitude recovery. When you practice unusual attitudes in the airplane, nose low condition, that's not a spin. So the difference of a spin and a spiral, a spin implies that you are in a stalled condition. Answer choice A. All right. A good question here, aerodynamics. The angle of attack at which an airplane wing stalls will remain the same regardless of gross weight. So the thing you're really picking up on here is that the angle of attack at which an airplane stalls will remain the same regardless of weight. The airplane always stalls for the same reason. It's because you exceed the critical angle of attack. So your airspeed that you stall at might change. Your stalling speed might change with weight, but the angle of attack is always the same. They usually say somewhere between like 16 or 17 degrees of angle of attack is the critical angle of attack for most general aviation aircraft. B is not the best answer choice. If the center of gravity moves forward, the angle of attack that you cruise at might change, but you still stall at the same critical angle of attack. Same thing with answer choice C. If you change the gross weight, you might change the angle of attack you cruise at, but you still always stall at the same critical angle of attack. So answer choice A, regardless of weight, regardless of center of gravity location, the airplane always stalls at the same angle of attack, critical angle of attack. All right, here's a good question. Standards. We need to know standards. What's standard temperature? What's standard pressure? Standard temperature, 15 degrees Celsius, 292 inches of mercury. That is standard pressure, standard temperature. Answer B looks like a good answer choice, 59 Fahrenheit. That's correct, but no, 292 millibars, negative. It's the wrong unit of measurement. You need to know millibars is 1013.2, 1013.2. 1013.2. That's the standard pressure in millibars. You'll need to know that for our next chapter as we move forward with weather and weather theory. Answer choice C is no good because it's saying 59, well, that'd be Fahrenheit. And then 1013.2, that's millibars, so that's correct. So the best answer choice here is A, 15 Celsius, 292 inches of mercury. And as we move forward into our next weather unit, we're going to learn how that temperature changes with altitude and how those pressure changes with altitude. All right, here's a good aerodynamics question. What force makes an airplane turn? Bum, bum, bum. It is the horizontal component of lift. So unfortunately, I have a lot of y'all selecting the wrong choice of a vertical component of lift. Vertical component of lift is what holds the airplane up. That's what makes the airplane climb. That's what holds us up. When we bank the airplane, when I bank the airplane, I am redirecting my vertical lift to now be horizontal lift. So what makes the airplane turn? Horizontal lift. We lose some vertical lift when we turn, but it is the horizontal component of lift that's actually going to turn the airplane. Lift turns the airplane, horizontal lift. Centrifugal force is the outside of the turn force. So that's almost what's kind of preventing the airplane from turning more rapidly. For a reaction, there's an equal and opposite reaction. What makes the airplane turn? Horizontal lift, horizontal component of lift. All right, I have some of y'all missing this question here. What is one purpose of the wing flaps? To enable the pilot to make a steeper approach to landing without increasing the airspeed. We've talked about that one a few times. Flaps, they let us have a steeper descent angle without picking up excessive airspeed. So I had some students selecting an incorrect answer here. to relieve the pilot of maintaining continuous pressure on the controls? That answer choice more corresponds with trim, T-R-I-M. That would be the function of trim. Trim would help relieve the pilot of having to hold force. So the better answer choice here, steeper approaches without excessive airspeed. That's the main purpose of flaps. Answer choice B looks bad. It says decrease the wing area. When you extend the flaps, you are increasing the wing area. Answer choice A, steeper approach to landing without excessive airspeed. All right, more aerodynamics. We love it. When are the 4 forces that act on an airplane in equilibrium? We've covered that today. It's during unaccelerated, straight and level flight. Answer choice B, if the aircraft's accelerating, then thrust exceeds drag. Answer choice C, if the aircraft is at rest on the ground, then there is 0 lift. There is 0 thrust, 0 drag, but the up and down forces are not equal. There is more gravity, more weight, and 0 lift. So the only time that they're equal in equilibrium is during unaccelerated, straight and level flight. All right, when landing behind a large aircraft, what procedures should be followed for vortex avoidance? We're talking about wingtip vortices, wake turbulence. So the idea is that it's a large aircraft, 747, you're landing behind. You do not want to get caught in their wake and their wash, so you need to try to stay above their flight path. That wake turbulence, wingtip vortices sinks, so you want to avoid getting beneath their final approach path. So the answer choice, stay above the larger airplane's flight approach path all the way to touchdown. So if I ever have landed an airplane behind a bigger airplane in front of me, I notice where their wheels touch, where they touch the ground, where they land, where they stop producing lift. And I make a note that I'm going to go touchdown 1,000 feet beyond their touchdown point. Answer choice B is bad. You don't want to stay below. Answer choice C is bad. You don't want to stay well below. You need to stay above their final approach path. And that's if you're landing. The more critical situation is actually when the larger aircraft takes off ahead of you and you have to take off behind, because it's difficult to do the correct thing. The correct thing is that you should stay above the larger aircraft's path. But the larger aircraft usually has multiple jet engines. It's very, very large, very, very powerful. So it's difficult for us to outclimb such a strong beast. So sometimes we do our best to stay above the path of an airplane climbing out. We might sidestep upwind to avoid their wake turbulence. Which aircraft has the right-of-way over all other aircraft? Aircraft in distress, 100% correct answer. Aircraft in distress. If there's an aircraft that has an emergency, they got the right-of-way. What condition is most favorable for the development of carburetor ice? We talked a lot about carburetor ice last time in our review session, and the idea is that 20 to 70 degrees Fahrenheit, high humidity. So it's actually more likely to develop carburetor ice on a warm, humid summer day. All right. We are operating in a Class Delta airspace. Each pilot of the aircraft approaching to land on a runway served by a VASI, visual approach slope indicator, shall maintain an altitude at or above the glide slope until a lower altitude is necessary for safe landing. That's the correct answer. B says stay high until the runway can be reached and to power off landing. Okay. C, maintain a 3-degree glide path until approximately half mile of the runway before going below the VASI. Okay, but the most correct answer, maintain an altitude at or above the glide slope until a lower altitude is necessary for safe landing. That's just the best answer choice. They all sound good, but that's the best answer choice for the FAA. Who is responsible for determining if an aircraft is in a safe flight? That's you. That's you, the PIC. You want to go fly that airplane PIC, you need to make sure that it's in a good, safe condition for flight. These other people, they may have roles in that, but it's you. You're responsible for determining if the airplane's safe and legal to fly. If you go fly that airplane that was not safe and not legal, the FAA is going to look at you asking you why you thought it was good, safe, and legal. All right, here's some true and falses for you. And unfortunately, I got some of you guys missing these as well, 50%. The FAR's, Federal Aviation Regulations, they require that your transponder be checked every 12 calendar months. That's a false. Transponders need to be inspected every 24 calendar months, every 2 years, 24 calendar months, transponder. Remember, we usually do this as AVIATES, AVIATES, annual, VOR, 100-hour, altimeter, transponder, ELT, static system. So those are kind of your acronym that us as private pilot applicants are trying to remember to get through check rides and stage checks. And the transponder is 24 calendar months, not 12. All right. Traffic off your right wing would be referred to as your 9 o'clock. That's a false. So the whole idea is that if air traffic control tells you traffic at 12 o'clock, that's straight ahead. If air traffic control says you have traffic at your 3 o'clock, that's off your right wing tip. If ATC says traffic at your 9 o'clock, that would be off your left wing tip. So you're trying to imagine that if you was looking at your airplane from above, looking down on your airplane, and you drew a clock, 12 hours all the way surrounding, if you had a bogey at your 6 o'clock, if you was in a wartime effort and the enemy fighters coming up behind you, that's when the other aircraft's at your 6 o'clock behind you. Air traffic control in a civilian world is usually not going to point out traffic behind you at your 6 o'clock because they want you to look for the traffic ahead of you. So don't worry about like your 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock. Possibly if it's in the left side of your windscreen, it might be at your 11 o'clock, 10 o'clock, 9 o'clock. So traffic off your right wing would be referred to as your 9 o'clock. That's a false statement. If it was off your right wing, it should be your 3 o'clock. Stop altitude squawk. That means to stop broadcasting your mode C. That is a true statement. Yes, it is. So on your transponder, we're lucky we have a Garmin transponder mode S capability. It's all automatic. It senses when we move. It senses when we land. It senses when we stop. It senses when we accelerate. It does all the different functions for you. But if you go and you rent an older style airplane, you would have the responsibility of turning transponder into standby, on, altitude. And so when it's on altitude mode, then you are broadcasting your altitude mode C. And if ATC is having issues with the equipment, they might ask you to stop your altitude squawk, stop broadcasting your mode C. You would then turn your dial from altitude, ALT, to just on, ON. So stop altitude squawk, that'd be an ATC request. That means stop broadcasting your mode C. That's a true statement. Okay, we got an ELT question. Emergency locator transmitters. They broadcast on 121.50 megahertz. That is a true statement. As you go farther in the aviation world, they're actually having some fancy new ELTs nowadays that are double that frequency. So that'd be like 243. So there's some new fancy ELTs in the world that broadcast on a UHF frequency, ultra high frequency, 243, but the standard VHF frequency, very high frequency that we're familiar with, is 121.50. That is the emergency frequency. They call that GUARD, G-U-A-R-D. So if you need to monitor GUARD, if air traffic control tells you to monitor GUARD, they want you to tune into 121.50. And you'll also remember that from our intercepting procedures. If a military aircraft wants to intercept you, you should listen for instructions on 121.50. And you should know that your ELT needs to be inspected every 12 calendar months. You should know that your ELT battery needs to be replaced or recharged if it's been used for more than 1 cumulative hour or half the battery life. You should know when is the proper time for you to be able to test your battery. To test your ELT equipment. And that's within the first 5 minutes of the hour. In the top of the hour, the first 5 minutes of the hour, that is when it's appropriate to test your ELT. So if there's an ELT signal going off at the first 5 minutes of the hour, people don't get too excited. That's the normal time for testing. All right, here's a question that I had a lot of y'all missing here. Chart supplements are updated every 30 days. That is a false statement. Chart supplements are updated every 56 days. So call it Airport Facilities Directory, AFD, call it Chart Supplement. Those are updated 56 days. So 30 days, false. That is not a true statement. 56 days is the correct answer. Okay, so here's one of the questions that we talked about at the beginning of our session. I had a few complaints about this question. At most Charlie and all Bravo airports, you must contact clearance delivery to get your transponder code, altitude, heading, departure frequency while you're on the ground. I have a lot of you guys giving me the answer ATC. So if you gave me the answer of ATC, I gave you half credit. So it says it's worth 3 points, so I gave you 1.5 points if you put the answer of ATC, because clearance delivery is a type of air traffic controller. So you're not incorrect to say clearance delivery. But what I'm telling you is that this is a question that you're going to see again and again. So you're going to have ABC multiple guess questions in the future where you need to know that the answer is clearance delivery. So at a Charlie or Bravo airport, in our example, when we went through this in class, I would say Evansville, because they're a Charlie airport. You would contact clearance delivery first, and they're the folks they're the air traffic controllers that are going to give you your squawk code, your altitude, your heading, your departure frequency. They're basically giving you your departure clearance, what you're going to be cleared to do once you take off, and after you get clearance to take off from tower, what your next few steps are going to be to get established on your cross country. Clearance delivery. Okay, when approaching a Class Echo airport for the purpose of landing, you should make your initial contact 10 miles out from the airport. Good, I like that one. Runway closures, TFRs, temporary flight restrictions, nav aid outages, other important information is published as NOTAMs, Notice to Airmen. Okay? The general rules and operating procedures for pilots are located in Part 91. Part 91 of the FARs, General Operating Flight Rules, General Rules and Operating Procedures. You should know that Part 61 is Certification of Airmen. Part 1 is Definitions and Abbreviations. Part 43 is Maintenance. Okay. I gave a lot of partial credit on this one. I actually probably gave a lot of full credit to a lot of the students. I gave half credit to some of the others. What are advisory circulars? Advisory circulars provide you with, these are the big words, non-regulatory guidance and information for a variety of subject areas. Advisory circulars could also explain methods for complying with regulations. So advisory circulars, you can see the word advice is part of the word advisory. So it's almost like the FAA is trying to give us good advice. Advisory circulars. I have a lot of students confusing NOTAM with advisory circular. So a NOTAM is more specific for a general airport, a general area. So like a NOTAM could be talking about runway closures. A NOTAM could be talking about taxiway outages. Whereas advisory circular is more giving you with non-regulatory information. So they're giving you like a memo on stall spin. They're giving you a memo on carburetor ice. They're giving you a memo on endorsements for flight instructors. So advisory circulars is the FAA trying to give you good advice, not specifically about one particular flight. Like if you're going to go fly across country and you need to get information about runway closures and outages, that is called NOTAM, N-O-T-A-M. That is a different topic than advisory circular, which advisory circular would be like an essay or a memo that's written up that you can go back and reference at any point in time, maybe about aerodynamics or weather theory or weather products, not necessarily a very specific flight, which would be more of their NOTAMs. So I had a lot of confusion here with some of the answers. I gave partial credit where possible, but there's a lot of y'all that got full credit as well. Advisory circulars. So when you're trying to take the real written test, remember, non-regulatory guidance. Advisory circulars, it's good advice, good guidance, non-regulatory guidance. All right, here's Airport Facilities Directory. We got a question. Here's a good problem for us. If you depart Eagle Creek at 10 Eastern Standard Time and it takes you 2 hours to fly west to BWG. What time will you arrive in Zulu? All right, so let's try to work this one out. I got a lot of people missing this question. My personal strategy, my favorite way, is to first convert everything to Zulu. So we're referring to the airport facilities directory. We're going to depart Eagle Creek at 10 Eastern Standard Time. So here's Eagle Creek Airport, and they're telling us that we are UTC, that's Zulu, Universal Time Coordinated. We are 5 hours away from Zulu time. If it was daylight savings time, we would only be 4 hours away. But when you read the question, we depart Eagle Creek Eastern Standard Time. It doesn't say daylight savings time, it says standard time, EST. So it is 10 local at Eagle Creek. It says UTC minus 5. So whatever the Zulu time is, you subtract 5 to get the local time. But wait a minute, we're starting with the local time of 10 local, 10 o'clock local. So we need to add 5 to figure out our departure time in Zulu. So we will depart Eagle Creek at 15 Zulu. We will depart Eagle Creek at 15 Zulu. It will take you 2 hours to fly to BWG. So 2 hours to fly, we departed at 15 Zulu. It took us 2 hours, so we will arrive at 17 Zulu. It says, what time will you arrive in Zulu? 17. So I could try to draw it out. If you want me to do like math class, right, where I draw up 10 plus 5 is 15 plus 2 is 17. I think I walked through it pretty clearly. Is there any feedback on this one for me? Is it good, bad, confusing still? Well, I'm getting no feedback, so I guess that you understand, and I guess I'll keep moving. Okay, here's another AFD question. If you want to get flight following from Bowling Green back to Eagle Creek, you contact blank on blank. So you had option choices like Louisville Radio, Memphis Center. It could be like 123.0, 133.85. The idea is, who are you going to contact to get flight following? If you want to get flight following, then that means you need to talk to somebody with radar. Like we discussed in class, here's an R in a circle for Memphis Center, approach departure controllers. So that R in a circle, that's who has radar around here. So it'll be Memphis Center, 133.85. So your correct answer is going to be contact Memphis Center on 133.85. And you know that because there's an R in a circle. That is who has radar to give you flight following. The other answer choice of possibly calling Louisville Radio, well, yeah, you can get a hold of Louisville Radio on 122.2 or 122.4, but they don't have radar. They are not air traffic controllers. They're not going to provide you with that service. So flight following, you need somebody with radar and air traffic controller, R in a circle. All right. Most of the people are getting this question right. What sectional chart is Bowling Green located on? Right here it says St. Louis sectional, top right-hand corner. Good job. Essay. I've been given a lot of full credit to this one. List and describe the C's below. You know, there's 5 of them according to the book: climb, communicate, conserve, confess, comply. As instructor, I add a few other ones like circle, check, compass. It says list and describe. So some of y'all are just typing the words, you know, circle, you know, climb, communicate, conserve, confess, comply. And then you didn't explain any of them. So if that's you, then you got half credit. But if you want full credit, you need to list and describe. All right, here's another time travel question. Time travel. All right. So we'll probably tackle this one, and then we'll probably be out of time, and we'll finish the rest of them next time and launch into weather. So let's see if we can tackle this one together. We're refer to figure 27. An aircraft departs at an airport in the Mountain Standard Time Zone. So Mountain Standard Time. So Pacific, Mountain Standard Time Zone. You depart Mountain Standard Time Zone at 16:15 Mountain Standard Time. You're going to fly for 2 hours and 15 minutes, 2-hour, 15-minute flight to an airport located in Pacific Standard Time Zone. So here's Pacific Standard Time Zone. The estimated time of arrival at the destination airport should be, and then the answer needs to be in PST. So the easiest thing for me to do is say I'm starting in Mountain Standard Time at 16:15. Let me see if I can zoom in. Control plus. Okay, so to convert from Mountain Standard Time to get to Zulu, to Universal Coordinated Time, it says we need to add 7 hours. Gosh, I see I'm already at 12:30. We will pick up with this question when we get back together. So I'm going to turn off my screen share. And I just want to say, you know, like, is there any general thoughts, questions, comments from the group? Some things I'm going to say real quick is like, we're moving forward. Next time we're going to be doing slideshows. We're going to be introducing material for weather theory, weather products. We're moving into chapter 6, weather. The idea is that we have the new homeworks are up. So you have vocabulary words, you have actual homework assignments. I'm gonna put up a short answer assignment. I haven't put that up yet, but you'll see that coming also through Blackboard. You have the practice written assignment. So every chapter we need to submit a new practice written. So moving forward, you know, you need to read the next chapter. You need to start doing those assignments. Chapter 6 is coming up, weather. We'll continue reviewing our test, our midterm exam next time. It won't take very much longer. We're almost done. Before I log it off, I'm open to any sort of feedback, thoughts, questions, comments from the group. Crickets.
No questions or concerns on my part.
Thank you for the feedback, Nick. Thank you for the feedback. Letting me know. Thank you. Awesome. So we got some feedback from Nicholas. He's pretty happy and satisfied. I guess everybody, he speaks for everybody.
I'm happy.
He's happy. Well, thank you guys for the feedback then. I'm going to log it off. I'll upload our video later. We'll get together Wednesday. Same idea, move forward. Study weather. Take practice writtens. Hope you guys have a great day. Be sure to get some good sunshine in your life.
Thank you.
Thank you.
Thank you.